Hello, today I have the honor to talk to Dirk van der Marel from the University of Geneva, who received the Frank Isakson Prize for Optical Effects in Solids this year. Congratulations, Dirk. The citation of your prize is for insightful experiments and analysis on a wide variety of quantum solids with strong electronic correlations in general and cuprate superconductors in particular using optical spectroscopy. Could you please describe your work that has led to the Isakson Prize this year?
In principle, it's a very long answer because it starts many years ago. But the superconductivity part has to do with this fantastic property of certain metals. If you cool them down to low enough temperature, that they go into a state of carrying current without any dissipation at all. So the current can go in a loop and just stay there for the age of the universe or longer. Now, the kind of experiments that we have been doing on this were motivated to find out why that happens, what's precisely the mechanism. Of course, many other people do it too, so we try to use a sort of original approach, complementary to what other people do. And usually the kind of questions we go for have to do with either the collective modes, the collective behavior of the electrons. So what happens if you make it oscillate, and how does it oscillate, which kind of modes of oscillation. And the other thing is to pose somewhat larger questions, like what happens to the kinetic energy, what happens to the potential energy, for those of you who know what it is, before you zoom in into very detailed questions. And so also the kind of thing we like to do is to get sort of yes or no experiments. So somebody has an idea and we try to find a way of testing this idea and see whether it's confirmed or not by the experiment. So by the scientific method you can move on to the next step and refine theories and something like this. So this we have done with optical techniques.
Mm-hmm.
You can use it. The nice thing about optical techniques can be done with very great precision. Also in temperature and in very precise spectra. And there's a lot you can read on that kind of spectra. There's a lot of precision.
Okay, thank you. Could you please let us know what you're currently working on to give us an outlook on what we can expect in the future?
Okay, we are currently motivated by, among other things, by what happens to the Coulomb energy in superconductors. This we do in collaboration with Tony Leggett, and he had the idea, and we were trying to test this idea. It can also done with optical experiments. And another direction, which is not directly related to superconductivity, at least not yet, has to do with the what we call non-local response, which means that if you shake here your material, then somewhere at the other end there may be also a response. And this is not very much done. One of the things you can study with it is how viscous a liquid of electrons is. And so normally people don't think in those terms about electron liquids, but actually you can. And there are a number of interesting consequences of that, also for the optical properties. So among others you may have actually negative index of refraction, which can be used to do very special kind of optical devices. So this non-linear stuff we are getting deeply into, but it requires completely different techniques than the usual ones.
Okay, great. Thank you very much, Dirk.